This is the curve that many of us deal with all the time. It's the classic exponential curve. Economists love to see it, especially if it's your portfolio, you love to see it. It's just exponential growth. And we see it with global population. This is the curve of global population from the year 1000 up to the present, showing the world's population growing exponentially. This is gross national product of the United States over the last 100 years, showing mostly exponential growth. I don't have the current down curve, no doubt, at the end, but this is what economists love to see. That's exponential growth. This is the concentration of carbon dioxide in the atmosphere from the year 1000 up to the present, showing fairly constant levels of carbon dioxide up until the Industrial Revolution, and the exponential increase in CO2 since the year approximately 1860. And this is the climate problem. So exponential growth, we see it in all sorts of things, good and bad. So this is a different curve, exponential growth with a peak and then a decline in something. We see this for a lot of different things as well. US oil production, and the whole debate about peak oil is related to this shape of a curve. Peak oil in the United States occurred in 1970. That is the peak of US production, and peak of US production happened and now it's declined. Now, could a huge investment in exploration make this curve turn back up in the United States? Maybe for a little while, but not forever. The debate is whether the world is heading toward peak oil, which is a non-renewable resource, which I'll get back to. But there's the curve, actual historical data for the United States. Here's the Dow Jones Industrial Average from 2002 to 2009. This is not a natural resource. This is a completely artificial thing, but there's the shape of the curve. Here's the herring catch globally from 1950 to 2008, showing that exponential increase in herring production, for those of you who eat herring, followed by a rapid decline as we overfished the resource, a natural resource, and the same thing for Atlantic cod. So here's the third curve. This is typically called the logistics curve. It's exponential growth followed by a leveling off, and potentially a constant level of something going forward, a sustainable level of something potentially. So here's a classic example of that. This is US penetration of telephones into the US market from over the last century. Fairly exponential growth, and then a leveling off when basically everybody had a telephone. And you see this kind of penetration curve for VCRs and CDs and cell phones and so on. It's sort of a classic technological curve, leveling off at some maximum. This is a curve of total withdrawals of water in the United States from 1900 to the year 2000. This is a curve that nobody really knows. Even in the water business, people don't understand this. We have exponential growth in the demand for water in the United States up until about the year 1980. And then something happened, and the curve leveled off. And the reality is, we use less water in the United States today for everything. Power plant cooling, flushing our toilets, washing our clothes, growing food, everything. We use less water in the United States today than we used in 1980. For a variety of reasons that I'd be happy to talk to you about later, that have to do with efficiency, that have to do with the structure of our economy, that have to do with limits on our ability to tap a finite resource, and so on. But let me dig into this water question a little more. And I'll do it in the context of oil and water. Let me talk about some of the characteristics of oil and water, aside from the fact that they don't mix. Okay, so let's talk about quantity. Oil, there's a finite amount of oil on the planet. and a finite amount of oil that we can extract economically. It's a question of technology, it's a question of price, it's a question of a lot of things, but ultimately there's a finite amount of oil. There is literally a finite amount of water on the planet, but in a sense, there's an unlimited amount of water on the planet at a cost, and that is the 97% of the world's water that's salt water in the oceans. Effectively, there's more water than we could ever want to use as a society for the things that we use water for. And so water is not finite in the same sense that oil is. Renewable or non-renewable? Oil is the classic non-renewable resource. Water, in some ways, is a classic renewable resource, although there are examples of non-renewable water on the planet. And I'll come back to that in a little bit, too, to describe what I mean by that. So think about water as a renewable resource, but with locally non-renewable stocks. And again, I will come back to that. Transportability. We move oil all over the place. Water can be transported, but not very far. Long-distance transport of water is not really economically viable. If you think about the economic value of a tanker full of oil, it's thousands of times higher than the economic value of a tanker full of water. And so there is a distance over which we transport water, beyond which it's much more economical to do something else, like desalination locally. Substitutability. There are lots of substitutes for oil at a cost, but there are lots of substitutes for the things that we use oil for. For most of the things we use water for, there are no substitutes. You can't grow food with anything but water. You can't survive on anything but water. There are ways of changing the amounts of water you require for different things. There are ways of changing the kinds of water you use, but water cannot be substituted for, and that's a big difference. Now, on this question of renewability or non-renewability, one way to think about it is non-renewable resources are classically stock limited. There's a stock of oil, and you can pump it out, but when it's gone, it's gone. It depends on the stock. Renewable resources are typically flow limited. The hydrologic cycle delivers water in a river every year, and that river has natural variability in how much water there is, and sometimes we have wet years and sometimes we have dry years, but when you use a unit of water on a river, it doesn't affect the amount of water you're going to get in that river next year. It's flow limited. You can't use more than the flow of the river unless you go to another source, but it's not stock limited, and that's sort of the classic definition of renewable versus non-renewable. Water uniquely exhibits characteristics of both renewable and non-renewable resources. Now, this idea of peak renewable resource, here's this curve again, this logistics curve. We can increase our use of a renewable water resource up to a point, and that point is the maximum amount of water that renewable flow supplies. And if you're using it sustainably, you can use it at that level forever. If you're not contaminating it, if you're not doing something else, you can increase that use to the renewable supply that constantly is cycled by the hydrologic cycle. You can use water in a non-renewable way. And there are certain stocks of water, groundwater resources in particular, that are not renewable on a time scale of interest to us. Now, there is renewable groundwater, and there's non-renewable groundwater. Renewable groundwater is groundwater that's recharged pretty quickly by rainfall. We pump it out, rain falls, recharges it, so we have renewable groundwater resources as well. But there are many groundwater resources that are non-renewable on a time scale of interest to us.